Hello everyone, and welcome back to thermodynamics. So I wanted to start this class just remembering why it is that we're supposed to care about thermodynamics. We've been spending a lot of time trying to figure out internal energies or specific internal energies or enthalpies or specific internal enthalpy, and I just want to remind you why it is that we're doing this. So thermodynamics is very important for mechanical engineers because a lot of the things that we use in real life are heat engines. We're taking heat and we're turning it into energy. So we're using thermal energy and turning it into dynamic energy. And we do this in a lot of different cases. So in things like nuclear power plants, automobiles, airplanes, we're going to learn how we do the opposite of this in things like air conditioners and refrigerators too. So the exciting stuff is coming, but before we do that, we need to learn these foundational skills. So when I think about a nuclear power plant or a coal-fired power plant, it's a series of different processes, from pumps to boilers. Remember, when you give mechanical engineers heat, oftentimes we want to boil water, because if we do that, we get an expansion as the liquid water turns into steam. We run that through a turbine, and it's that turbine that gives us usable energy, because as that steam expands over those fan blades, we get a spinning shaft. And we can turn that into mechanical work, or we can hook that up to a generator with our electrical engineering friends and then get electrical work as well. So now, after we go through the turbine, we have this low quality steam that we want to pass through a condenser to turn it back into a liquid so we can pump it back up again. So there's a series of processes. Now, of course, nuclear power plants are more complicated than that, but they are a series of processes. So I like to think of them as Lego blocks, where if we could understand each one of these processes, which is like a Lego block, then we can stick these blocks all together to come up with some really interesting and valuable technologies. Things like power generation stations. But before we understand the Lego block, which is like a process, we need to be able to fix a state. And that's really what we've been focusing on, is how do we understand each of our little pips on top of a Lego block. So I know that it can feel a little bit tedious or drawn out right now, but remember, we're trying to learn how to make blocks, and then once we make blocks, we can start to make some really cool things, like power plants or airplanes or cars. Now, one of the most maybe tedious parts of what we've been doing is this double interpolation. Now, double interpolation happens a lot when you're talking about compressed or subcooled liquids. And that's because the tabulated data here is really sparse, because many of these properties become weak functions of temperature and pressure when we're talking about subcooled liquids. So we did talk about how to do these double interpolations. We can interpolate. In this case, we found our interpolation factor A between these two pressures. So with that interpolation factor, we made our own table at 80 bar, and then we had to add a row in that table with our known enthalpy, and then we used another interpolation factor to fill in that table and find out what our temperature was between 40 and 80 degrees. Now in this case, it was pretty close to 40, but you can see here our numbers didn't change all that much. And then we could plot this state point on PV and TV diagrams. We felt pretty good about it because we fixed all the states, but we probably spent a little bit more effort than we needed to. So today on thermodynamics, we're going to talk about specific heats and how we can use specific heats to maybe save us a little bit of time, because honestly, double interpolation is pretty tedious. First, we want to just review what's going on in our closed systems. When we have closed systems, we have three questions we want to answer. We want to know what's in our system. Is it water? And if it's water, what state is it in? Is it liquid? Is it vapor? Or is it some mixture of the two? Is the system open or closed? Can mass come in or out of my system? And so far, we only know how to deal with closed systems. And then we want to say what happens to the system as we move between our states. How much heat do we get and how much work do we get? So because our system is closed, we get this version of the first law, where the change in energy in the system is equal to the heat that comes in minus the work that goes out. But we end up making some assumptions to change this equation a little bit, because usually in the processes we're going to talk about in thermodynamics, potential energy and kinetic energy are much smaller than the change in internal energy. So now our equation on the left-hand side becomes the change in internal energy, and what we need to do is find work as the integral of P dV. We'll find delta U by looking up specific internal energy on tables and multiplying by the mass in our system, and then we'll use all of that information and the first law to find the heat that comes in or leaves our system. We weren't sure how to find delta U until a couple of lectures ago, but now we see that we're going to use our tables. If we have a two-phase mixture, then we use table A2 or A3, and maybe we interpolate with quality. Sometimes we'll be given quality, sometimes we'll be given another property which we can use to find quality, and then use that to find the specific internal energy. Sometimes the material inside of our system is a single phase, like a liquid or a vapor, and then we use table A5 or A4. In these different tables, what we look for is we look for the right subtable that has the pressure that we're looking for, and then we find an interpolation factor between rows on our table, or maybe between tables if we don't have a table with the right pressure. And then we get an expression that actually looks a lot like our quality expression to find specific internal energy at the given temperature we're looking for. Now, like we've said, unfortunately for subcooled liquids, we have pretty sparse data. So a lot of times we would have to do double interpolation if we're using those tables. Turns out I don't always want to have to do double interpolation, and if I could avoid doing all that algebra, I probably would. It's not that it's all that hard, it's just that it takes a long time. So do we have to do double interpolation? And the good thing is, if we're in that subcooled liquid region, we don't always have to do this, because there's another way where we can get a good approximation. And to do that, we need to look at specific heats. We have two different types of specific heat. So one is specific heat at constant volume, or C sub V, and the other is specific heat at constant pressure, or C sub P. Then we also have this ratio K, which is Cp, Cp is always larger, over Cv, so K is always bigger than 1. So now we need to see what the actual definitions of these specific heats are. Cv is the rate of change of the specific internal energy with temperature. So it's kind of the slope. If I was plotting U as a function of T, it's the slope of that line. Cp is almost the same, except that it's the rate of change of enthalpy, specific enthalpy, with temperature. So remember, enthalpy H is U plus PV. So Cp is always a little bit bigger than Cv. Now for subcooled liquids, for closed systems, what we're interested in is specific internal energy. So we're going to focus on C sub V, or Cv. So Cv has this definition, which is the change in U divided by the change in T. Or if we separate that out, we can get C times dt is equal to du. We're going to integrate both sides. And if we assume that Cv is approximately constant, now this isn't exactly true, but it's probably a weak function of temperature, then we get Cv times the integral of dt is equal to the integral of du. So after we integrate this, we get that Cv times delta t is equal to delta u, or at least approximately equal if we assume that Cv is constant. We can do the same thing with Cp, it's just that when we get Cp times delta t, we get delta H. So here, now we have different expressions for the change in specific internal energy as a function of the change in temperature, and the change in specific enthalpy as a function of temperature. Now it turns out that for subcooled liquids, Cv and Cp are very weak functions of temperature, so they don't change very much as long as we're still a liquid. So things do start to change a lot once we change phases, but but as long as we still have a liquid, these approximations are pretty good. So if I know the change in temperature of a subcooled liquid, then maybe I don't have to double interpolate everything. I can just say, what's CV times the change in temperature that we're looking for, and that will give me the change in the specific internal energy. So for incompressible substances, including subcooled liquids, CV is approximately equal to CP. So when we're talking about closed systems for liquids, if you looked it up on a table, sometimes it won't even have separate values for CV and CP. Sometimes there'll just be one value for a specific heat, because these tend to be approximately equal for subcooled liquids. So sometimes, though, we're not looking for a change in temperature. I just want to know what the specific internal energy is at a given temperature. So this is a little bit like our state 6, although we didn't know the temperature at the time. But we have this point, which is clearly in the subcooled liquid region. If I knew the temperature, how could I find the specific internal energy if it wasn't given? In this case, too, we also knew the pressure. So when we have a TV diagram, this is what a constant pressure line looks like. It slopes up until it hits the saturated liquid line, and then it's flat, because remember, temperature and pressure are dependent. If we know one, we know the other, as long as we're under the vapor dome. And then it slopes up again once we're in the superheated vapor region. So if I wanted to go from state 6 that we had last time right up to the saturated liquid line, I could find out the saturation temperature at that pressure, and in this case, it's 294.1 degrees Celsius. Now, I can also find the saturated liquid specific internal energy, and that's 1,356. So I could use this new equation that I have, that the change in specific internal energy is equal to CV multiplied by delta T. I look up CV, and in this case, it's 4.38 kilojoules per kilogram degree Kelvin. Now, remember if we're checking our units here, you'll notice that a lot of times we'll have Kelvin in the denominator here, but we'll multiply by a temperature difference. Now, because it's a temperature difference, I'm okay to use Kelvin or degrees Celsius here. If you had a thermometer, and maybe on the left-hand side of the thermometer you had degrees Kelvin, and the right-hand side of the thermometer you had degrees Celsius, those lines wouldn't line up, particularly if you're looking for 0 on both of those thermometers, right? They're 273 degrees apart. But if you looked at the spacing between the lines, it's the same. So the change in temperature in Kelvin is going to be equal to the change in temperature in Celsius. The same thing is going to be true in imperial units. If we had the change in temperature in degrees Rankine, which is like the imperial equivalent of Kelvin, where 0 is absolute 0. So the change in degrees Rankine is always going to be equal to the change in degrees Fahrenheit. So here, now I could go back from this state on the saturated liquid line, which I can look up fairly easily on my two-phase tables. Or if I wanted to, I could also look this up on the subcooled liquid table if I had the right pressure. I wouldn't interpolate to get this because it's pretty easy usually to get on the two-phase tables. And I know this temperature, and I know the temperature that I have down here. I can use delta U is equal to CV times delta T. I can isolate for U6, and if I do the math here, then I found that my approximation for U6 was 200.5 kilojoules per kilogram. Now, I can see that there is some uncertainty here, but at least I got an answer. So we're not right, but we're in the ballpark. So sometimes that's reasonable. Again, as an engineer, part of your job is to figure out how accurate you need your answer to be when you're talking about a real-world problem. You need to know the accuracy that's required for whatever application you're working on. In this case, we have an error or an uncertainty of about 15%. But what if we don't want delta U? So if we have any particular pressure, we can assume that the specific internal energy at a temperature for a subcooled liquid is approximately equal to the specific internal energy of the saturated liquid that's at the same temperature. So here, let's look at this. So if we're at 1 atmosphere and we have a temperature of 100 degrees, then we know that the specific internal energy is 418.94. But if I have that same temperature and my pressure goes up to 25 bar, my specific internal energy doesn't change very much. In fact, my error here is 0.2%, which is really small. If I go up to 50 bar, my error goes up to 0.3%, 75 bar up to 0.5%, 100 bar up to 0.7%. You get the picture here. It doesn't change very much the specific internal energy at this temperature as I'm moving up my pressure a lot. So when we stayed at constant pressure and we found the saturated liquid specific internal energy and we moved down to the specific internal energy at a given temperature at the same pressure for the subcooled liquid, we were getting errors of about 15% in that case. But here, if I use this strategy, then my error is much lower. So here, this is a better strategy if I'm trying to find specific internal energies for subcooled liquids. It's also nice that it's easier because I can just go to whatever table, I think it's table A2, which is my two-phase tables, and I just look up whatever temperature that I have, and I write down UF. And we see that it's almost the same in all of these cases. So this is all within 2%, and this is a range, a 300-fold range in temperature or in pressure. So here we're pretty good if we use this approximation. So I would encourage you, if you're trying to find specific internal energies for subcooled liquids, to use this method because it's the fastest and it's the most accurate. If we're drawing this out on our table, basically we're saying that this point here, which is our subcooled liquid that was at a given temperature and a pressure, has approximately the same specific internal energy as the saturated liquid that's on the same temperature line. So it's essentially the same as this open circle that's over there, which I can find very easily. So in that case, my UF was 174.9. And we're not typically looking for enthalpies yet, but the specific enthalpy also works the same, where I can find the specific enthalpy of a subcooled liquid just by looking at the saturated liquid at the same temperature. I get slightly more uncertainty or slightly more error if I do that, but it's still a pretty good approximation. The good part is that doing this makes our lives easier. It's less double interpolation. The bad part is that the solution has a higher degree of uncertainty. So while the specific internal energy is a function of temperature, it's not a function of temperature alone. Pressure matters too. So as the pressure starts to change, our uncertainty grows. And this is more true when we're talking about enthalpies, because pressure is more important when we're talking about change in enthalpy, but it's important for internal energy too. And this is part of the reason why we always want to write down our assumptions, so that if we go back and for some reason our answer doesn't look physical, or after you do an experiment based on your calculations, you find that the experiment doesn't really agree with your analytical work, then you can go back and you can see which assumptions do you sort of trust the least, which ones do you think have the highest degree of being wrong. The other good part is that this is a reasonable assumption in many engineering applications. So we're teaching you things that are actually practical to use, but looking up the data will always give you more accurate results. It's just that here, when we're talking about subcooled liquids, particularly with specific internal energies, but for enthalpies too, the increased accuracy you get is not very much. So this is a pretty good assumption to make. So now we're going to do a bit of a problem that talks about the first law, now that we know a little bit more about how to find U. So as shown in this figure at the bottom, a system consists of a copper tank whose mass is 13 kilograms, 4 kilograms of liquid water, and an electrical resistor of negligible mass. The system is insulated on its outer surface. Initially, the temperature of the copper is 27 degrees Celsius, and the temperature of the water is 50 degrees Celsius. The electrical resistor transfers 100 kilojoules of energy to the system. Eventually, the system comes to equilibrium. Determine the final equilibrium temperature in degrees Celsius. So we'll follow our solution process. We want to write down our known information. We have a mass of copper, 13 kilograms, a mass of water. We have the mass of the resistor, which we're going to assume is very small, approximately 0, compared to the mass of the copper and the mass of the water. We know the initial temperature of the copper is 27 degrees Celsius. The initial temperature of the water is 50 degrees Celsius. We know that some amount of time passes between 1 and 2, and it's enough time that the system comes to equilibrium. So I don't know that we've used that word before, equilibrium. So here it means that the temperatures here will become equal. So we'll get to a point where everything is equal, right? So it's at equilibrium. This typically takes a fairly long time. If you think about you boil some water for macaroni and cheese, but you forgot to put the macaroni in it or something, or maybe you just left it on the pot after you stopped cooking it because you had to go outside and do something. Eventually, over time, the macaroni and the liquid in that pot will get back to room temperature. So then everything is at equilibrium again. The energy from the resistor is 100 kilojoules into the system. We're going to also assume that our system has an insulated surface around it so that no heat or work can come in or out. What are we required to find? We want to know the temperature in degrees Celsius once everything hits equilibrium. So here I have my system, which is perfectly insulated. That's, I guess, what this speckled border is around my system. I have a resistor, which is heating up the copper, and then I have liquid water on the inside. So this is like an electrical heater, right? I know if I draw out my temperature and my time here that I have copper, which is initially at 27 degrees Celsius, water, which is initially at 50 degrees Celsius, and eventually they're going to come to some equilibrium temperature. But I'm adding energy into the system, so I don't know if this temperature is going to be between these two values or potentially above this value too. So I'm going to make two different tables to solve this problem. The first is a state table, which we've been doing a little bit. So I have the water, right? I know its initial temperature, and I have the copper's initial temperature, but I'll also get some information for the water and the copper at the final temperature as well. And then I'll make a process table as I go from state 1 to state 2, how much heat is added and how much work leaves the system. So let's start. We're going to state and justify some assumptions. So here, I'm going to assume, because as we move from state 1 to state 2, that everything is insulated so that there's no heat coming in or out of my system. I know, or at least I'm going to assume, that the temperature of the copper and the water at state 2 is going to be equal. So there's really only one T2. So if I'm looking at the state of my different materials here, so I have two different materials, one is copper and one is liquid. So here I'm using X, which we've typically been reserving for quality, and I would probably encourage you to do that. But here I'm just trying to say what the phase of my different materials are. So the copper, I think, is going to remain solid. I don't think we're putting enough energy into the system for the copper to melt. We're probably also not putting enough energy into the system for the liquid to boil. So I'm going to assume, at least initially, that I'm moving from one subcooled liquid state to another subcooled liquid state. We'll check, because I'm going to assume that my pressure is approximately atmospheric pressure here. So if my temperature gets above 100 degrees, then maybe I'll have to revisit this assumption. That's why it's an assumption, because I don't really know if it's true, but I'm going to guess. At the end of the problem, I'll check. Here, my specific heats, I'm going to say, are constant for both the water and the copper, so that the specific internal energy is changing on a constant slope with temperature for both the water and the copper. But those specific heats will be different because they're different materials. And for the delta U, so the change in internal energy, I'll make the assumption that the water is liquid, so that it moves from one subcooled liquid state to another subcooled liquid state. So I can use CV times delta T. For the copper, which is a solid, we can use the same equation. So my solution My first law, I'm going to assume that the kinetic and potential energies are small, so I'm only interested in delta U. So the left-hand side of my equation here becomes the change in U for copper plus the change in U for water is equal to Q, so the heat that comes in minus the work that goes out. Now, the important thing here is that when we're talking about these changes in internal energy, we always end with we start with the end state and we end with the beginning state. So this is U at the end minus U at the beginning. So it's always going to be U2 minus U1. Now, we've said that the system is insulated so that there's no heat coming into our system. So now when I apply my approximations that I can use CV times delta T to find delta U for both of these systems. But if I say CV times delta T, that gives me the change in the specific internal energy. So I want to multiply by the mass, and I didn't keep the subscript here, but in this term where we're talking about the copper, this is the mass of the copper. And in the term where we're talking about the water, this is the mass of the water. So this is nice. I know most of the things on the left-hand side. I know the mass of the copper. I don't know T2, but I do know T1. I know the mass of the water. I don't know T2, but it'll be the same as T2 for the copper. And I do know T1 for the water. So the things that I don't know here are the specific heats, T2, and the work. And this is not too bad. I can look up the specific heats in the textbook. So the specific heat for copper is 0.386 kilojoules per kilogram Kelvin. Now, the specific heat for water is 4.18 kilojoules per kilogram Kelvin. Now, you see that there's a pretty big difference, more than a factor of 10 between these two numbers. Copper is a great conductor of heat, so it doesn't take too much energy to increase the temperature of copper. The temperature of water, as we know, right, we keep saying a watch pot never boils. It takes a lot of energy to increase the temperature of water by even just a degree. The trickier part is the work. So this energy that's coming in electrically could be used to move something. So to apply a force over a distance. So we can think about this as work if we want. Now, this is energy that's coming into our system. So if we think about this as work, then this would be work in to our system, and work in is negative. I could have set this problem up so that I thought about there being no work here, and I thought about this energy coming in as heat. And if I did that, heat in would be positive. So if I thought of this as a Q, then the sign would change because of the sign conventions, right? Heat in is positive and work in is negative. So it's going to end up being the same on the right-hand side of my equation, 100 kilojoules, no matter which one that I choose. So don't get too worked up if you would have thought that this would have been a heat and not a work. I don't know what T2 is, but I do know that it's the same for copper and for water. So here, if I work this out, I could isolate T2. That's the only thing I don't know now. So I know the mass of copper. I know the specific heat of copper. I know T1 of copper. I know all that same stuff for water, and I know the work. So the only thing that I don't know here is T2. So I can go through and I can isolate this equation for T2. And I can see that T2 is 49.3 degrees. That's it for today. I look forward to seeing you next time on Thermodynamics.